Hey everyone, welcome back. Last time we saw the coin change problem, where greedy failed and dynamic programming saved the day. Today we flip that story completely. The activity selection problem is about scheduling. You are giving a list of activities, each with a start time and an end time. You have a single resource. Think of it as one meeting room, for example, one CPU, or one person. And you want to select the maximum number of non-overlapping activities. Formally speaking, we can say, given n activities, each with a start time Si and finish time Fi, select the maximum number of activities that can be performed by a single resource, where no two activities overlap. And here's the exciting part. A simple greedy strategy, always picking the activity that finishes earliest, is probably optimal. Let's see where is it used in real world. We can use activity selection for booking the maximum number of meetings in a conference room, for example, or we can use it for maximizing the number of jobs completed on a single processor. The activity selection is the foundation of interval scheduling theory. It shows that sometimes the simplest greedy rule, such as finish earliest first, is all you need to guarantee an optimal result. Let's see how greedy solve this problem. First, we are starting with sorting all activities by their finish time in ascending order. It is really important that we should sort them based on their finish time. So this is the key point. Then I am declaring my variables. First, I need to have a final selected tasks list. It will hold my selected task at the end and I will return it. And I need to look for the time when the last selected task is going to finish. Now, initially, it is going to be 0. Then I am going into the main loop, and for each possible activity sorted in ascending order based on their finish time, I'm looking at their starting time. If the starting time is later than or equal to the last finished task's final time, then I am adding that activity in my selected list. Since I add a new activity, I am updating my last finish time, and at the end of the main loop, my selected list will give me the maximum activities I can do. Actually, what we are going to do is that at every step from the remaining activities, we are picking the one with the earliest finish time that is compatible with the last selected activity. So that's the whole thing. So no other choice can do it better. Any activity that finishes later leaves strictly less room. Let's walk through with an example. Given 7 activities with the following start and finish times, we have A1, A2, A3, A4, up to A7. The goal is to find the maximum number of non-overlapping activities that can be selected. So here's what all 7 activities look like plotted on a timeline. Each bar here stands for one activity's duration. You can immediately see that many activities overlap. So my job is to pick as many activities as possible without any two bars colliding. The first step is to sort all activities by their finish time in ascending order. Since my activities happen to already be in this order, I'm not touching the order. Then I will loop through the sorted list and start building up my selected list. I am initiating my variables, which is the last finish time, which is going to be 0 initially, and my selected list, which is going to be empty. The first activity in the list is A1, which start and finish time are 1 and 4 respectively. Since the last finish time is 0, which means it's before the start time of A1, I'm going to add A1 into my selected list. And after selecting A1, I'm going to update the last finish time too. So in the beginning it was 0, but I need to update it, so it's going to be 4. My next possible activity is A2, starting at 3 and finishing at 5. Since the last finish time is after the start time of this activity, I can't select it. So I will pass. In the same way, I can select A3 as well since it starts way before the finish time of the last selected activity. We can add A4 since it starts after the finish time. And after I edit, I should also update the last finish time variable, which is going to be 7 in this time. Then again, I can't add A5 or A6 because they are overlapping with the previous selected activities. So I am passing them. And finally, we can add 7, A7, because it starts at 8, which is after the finish time of the previous activity. And we are done. So all activities are processed. And at the end, 3 activities are selected in total, which are A1, A4, and A7. They are perfectly non-overlapping, back-to-back on the timeline. Maximum activities are selected, which, as we say, 3. And we need to say this is probably optimal, and there is no selection of 4 or more mutually compatible activities exists in this input. This is important. This is kind of a proof that we need to give after solving the problem. Actually, we need to do that after every greedy problem. We need to prove that it is the optimal one. In dynamic programming, we don't need to do that because recurrence is always solving it for us, so we don't need to prove anything. Now that we have seen both coin change in the previous video, where greedy fails, as you remember, and activity selection, where greedy is perfect, let's summarize when each approach is appropriate. We need to use greedy if local best means global best. If it is not, then we should use dynamic programming. What does that mean? The key question to ask in order to decide whether or not we can use greedy is, if I make the locally best choice right now, can future choices still reach the global optimum? If the answer is yes, then we can use greedy. If it is no, then we should use dynamic programming. In greedy, we need to prove that this is the optimal result by using exchange arguments. However, in dynamic programming, we don't need to prove anything because recurrence guarantees correctness. There is one important thing in activity selection, which is we should always sort by finish time, not start time or duration. So this is the non-obvious insight that makes the algorithm work, so it's very important. Next, we will see Huffman encoding, which is another greedy algorithm. This time, it applied to data compression, which is very important. And we will see how greedy builds an optimal prefix-free code from bottom up, and why it's used in real-time compression formats like zip or JPEG. If this helped, like and subscribe, and drop a comment with a real scheduling problem from your own life where this could apply. See you in the next one.